Hi folks, this is the next video for Year 1 Further Maths Pure, and we're looking at 8b, the divisibility tests. So let's go straight in. Example 4, prove by induction that 3 to the 2n add 11 is divisible by 4 for all n where n is in the set of positive integers. So I use the function notation, and I'm going to set up this function called f. First step, of course, let n equal 1. 3 to the 2 plus 11, which is 20. True for n equals 1. And then remember the assumption step, assume true for n equals k. So we're saying that f of k, which is 3 to the 2k add 11, is divisible by 4. And remember what I want to do. I want to show that if this is true, then work out f of k plus 1. Now my strategy is slightly different to that in the book, and of course you can take whichever one you want. So I'll write this out again with k plus 1 instead of k. Now the strategy is to get an f of k here and to see what's left over. Consider 3 to the 2k plus 2. Well, that's just 3 to the 2k multiplied by 3 squared, which is 9 lots of 3 to the 2k. So I'm going to write it like that, 9 lots of 3 to the 2k. I want to take out an f of x, so I'm going to split this into 8 lots of 3 to the 2k plus another lot of 3 to the 2k, because then I can see that that is my f of k, not f of x. And that's the strategy with all of these divisibility ones. So it's f of k plus 8 lots of 3 to the 2k. Move up the page a bit. Remember, I want to show that it's a multiple of 4, so I'll write it as a multiple of 4. Now, since that's divisible by 4, and I'm adding on a multiple of 4, the whole thing must be divisible by 4. So I've proved it. If it's true for f of k, then it is true for f of k plus 1. So let's write our conclusion. If true for n equals k, then true for n equals k plus 1. Since it's true for n equals 1, then let's write our conclusion. 3 to the 2n plus 11 is divisible by 4 for all n where n is a natural number. Or of course, remember, I could have used z plus. Somewhere, I guess, in my conclusion, I will say by mathematical induction. But I don't think you'd lose a mark if you didn't explicitly write that bit. Okay, example 5, exactly the same strategy. N cubed minus 7n plus 9 is divisible by 3. So let's set up the function. Set n to 1. true for n equals 1. Assume true for n equals k. And then we're going to say if it's true for n equals k, blah, 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 blah. So let's work out f of k plus 1, k plus 1 cubed minus 7, k plus 1 plus 9. Binomial expansion. So if you haven't done that, just trust me. K cubed plus 3k squared plus 3k plus 1. Expand these brackets. Again, I want to take out an f of k if I can. Well, there's my k cubed minus 7k plus 9. What have I got left? I've got 3k squared left plus 3k. Didn't take out the 1, didn't use the minus 7. So f of k, add 3k squared plus 3k minus 6. Because I want to prove it's divisible by 3, I'll write this as a multiple of 3 so I can take out my factor. Now this is valid because this will always be a whole number. What I have left in my bracket I need to make sure will always be a whole number. And of course, for the last example, that would always be a whole number. Clearly it's going to be here as well. So that must be divisible by 3. Because, I should have said, because we've assumed it is. This is a multiple of 3. And so I can say that f of k plus 1 is divisible by 3. So I've shown that if f of k is divisible by 3, then f of k plus 1 is also divisible by 3. And since I've got a value of k for which it's true, I can write my conclusion. So if f of k is divisible by 3, no, let's not write that. If true for n equals k, then true for n equals k plus 1. Since it's true for n equals 1, then by mathematical induction, what did I want to prove? It's n cubed minus 7n plus 9 is divisible by 3 for all n, where n is a positive integer. Reminder, the symbol for all n. I could have just written that. Okay, same strategy for example 6 with one extra twist. Let's go through it. 11 to the n plus 1 plus 12 to the 2n minus 1 divisible by 1, 3, 3. So same dance again. Set up my function. N equals 1. Two minus 1. Better check this out on my calculator. Good. True for n equals 1. Let's assume true for n equals k, so that f of k, which is 11 to the k plus 1, blah, 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 That was just stupid, sorry. 11 to the k plus 1 plus 12 to the 2k minus 1, I got ahead of myself, didn't I? Is divisible by 133. So the f of k plus 1 well, that's 11 to the k plus 1 plus 1 plus 12 to the 2k plus 1 minus 1. Let's sort that out. In fact, I'm going to leave that as it is because remember what I want is to take out my f of k. So I'm going to write it like that. 2 to the k plus 1 minus 1. Well, that's just 2k plus 2. 2k plus 1, isn't it? And I'm going to write this as 2k minus 1 plus 2. And the reason that I've done that is because I need that 2k to the minus 1, because remember, I want to take out my f of k. So 11 times by 11 to the k plus 1 plus, well, this will be 12 to the 2k minus 1 times by 12 squared. So 11 to the k plus 1 plus 144 12 to the 2k minus 1. Now, you might want to pause, rewind, go back, get your head around these last few steps. The reason I've done it is because I want to take out f of k. What I can actually do is take out 11 f of k's. So I'm going to do that. So I'll split this into 11 lots of 12 to the 2k minus 1 and 133 lots of 12 to the 2k minus 1. Because of course that's 11 f of x's. So here we go, 11 f of x, well that must be a multiple of 133, and 133 lots of some whole number. So that must be divisible by 133, as is that. So f of k plus 1 is divisible by 133. So conclusion again, since true for, no, if, there you go, true for n equals k, then true for n equals k plus 1. Since true for n equals 1, then by mathematical induction, and our conclusion needs to be what it was I was setting out to prove, 11 to the n plus 1 plus 12 to the 2n minus 1 is divisible by 133 for all n where n is a positive integer. Okay folks, have a go at 8b. Get back to me if you need anything.